Hello everyone. Now again we will apply the basic concepts of electrical machines that we already learned in electrical machines 1 and electrical machines 2 to solve the numerical questions of end semester examination of winter 2017. So let us begin with the first question. Question 1A for 5 marks. A 5 kVA 200 volt star connected 3-phase alien pole alternator with direct and quadrature axis reactance of 12 ohm and 7 ohm respectively delivers full load current at unity power factor. Calculate the excitation voltage and full load regulation neglecting resistance. So this question we have already seen in summer 2018. The same question, but the condition is that here we have to find out the regulation at unity power factor. Q is 5 kVA, line voltage is 200 volt, XD is 12 ohm, XQ is 7 ohm, cos phi is 1, so phi is 0 degree, sin phi is 0. And then we have to determine the excitation voltage and full load. So the equations to be used that we know already, that is voltage per phase is the ratio of line voltage to root 3. Then apparent power Q is equals to root 3 times the line voltage and line current. Full load current I is equals to rated kVA multiplied by 1000 divided by root 3 VL. Tan delta Ixq cos phi divided by V plus Ixq sin phi. ID I of sin I multiplied by sin of phi plus delta. Excitation voltage E naught is equals to V cos delta plus IDXD, as here armature resistance is neglected, so IQRA drop is neglected. Then full load regulation is equals to E naught minus V divided by V. So the voltage per phase is 115.47 volts. Then put the calculated value of the per phase voltage here to find out the regulation, and then the excitation voltage E naught, right? Then put the value of phi is equals to 0 and delta, we get the ID as 14.429 amperes. So the regulation is 50.93%. Now the next question is question 2B for 5 marks. A 3-phase star connected alternator rated 1600 kVA 13,500 volt delivers output power of 1280 kilowatt. The synchronous impedance of alternator is 1.5 plus J30 ohm per phase. Calculate percentage regulation at full load condition for following power factors, that is unity and 0.8 lagging. So write down the given data first. Q is 1600 kVA, VL is 13,500 volt, P is 1280 kilowatt, power factor is unity power factor and 0.8 lagging, and the synchronous impedance is given as 1.5 plus J30 ohm in rectangular form. So first we'll see the equations to be used to determine the percentage regulation at unity power factor and 0.8 lagging power factor. So as we know that power factor is nothing but the ratio of kilowatt and kVA, right? So using that we can find out the kVA, that is load in kVA. Then phase voltage is the ratio of line voltage to root 3. Then Q is equals to root 3 times the VLIL. Full load current I is equals to rated kVA multiplied by 1000 divided by root 3 VL. Then open circuit voltage per phase as per the synchronous impedance method for the determination of voltage regulation of an alternator E naught is equals to square root of Vp cos phi plus IRE whole square plus Vp sin phi plus IXS whole square. So here we have to take phi positive for lagging, negative for leading, and 0 for unity power factor. So remember this, how to calculate the E naught for lagging, leading and unity power factor. So by putting the cos phi as 0.8 and taking the kilowatt rating as 1280, so we can calculate the load in kVA as, that is 1280 by 0.8 is equal to 1600 kVA. Then voltage per phase by taking the ratio of 13,500 by root 3 is 7794 volts. Then full load current I is equals to load in rated kVA that we have calculated, that is 1600 volt multiplied by 1000 divided by root 3 into 13,500 volt, that is the line voltage. The full load current is 68.42 ampere, so put that values, that is Vp is equals to 7794, cos 5.8, I 68.42 amperes, and the given value of effective resistance per phase as 1.5, and take the whole square. Then again Vp 7794, sin phi as 0.6, then I 68.42 and excess is 30 ohm per phase, and take the square of the terms, and then open circuit voltage per phase is 9244 volts. So put the value of that in the percentage regulation equation, that is E naught minus Vp by Vp into 100. Then we get the regulation as 18.6%, and that is positive because it is calculated for 0.8 lagging power factor. Now the second condition, we have to determine the voltage regulation for unity power factor. So using the same equation, same concept, just put the value of cos phi as 1, then get the load in kVA, that is 1280 kVA. Then voltage per phase will remain same, that is 7794 volts. Load current will change here because the rated kVA is changed, that is 1280 into 1000 divided by root 3 into 13,500. So the full load current is 54.74 amperes. Then open circuit voltage per phase. So here by putting the value of Vp as 7794 volts, cos phi 1, current 54.74, and the given value of effective resistance per phase as 1.5, then take the square of that, and then again sin phi as 0 and excess as 30 ohm per phase. So the open circuit voltage per phase, that is E naught is equals to 12,291 volts. Put that value in equation, E naught minus Vp by Vp into 100. Then we get the percentage regulation equal to 57.69%, and it is very large, and it is for unity power factor. Now we will see the same question that is asked in end semester examination of summer 2018, but the conditions are different. Now here the conditions that the full load regulation is to be determined at unity power factor and 0.8 leading. In the previous question we have seen that it is determined for unity power factor and 0.8 lagging power factor, right? So the same given data, then same equations we are using here, but we have to take here in open circuit voltage per phase, that is E naught in equation, that cos phi as 0.8 but the sin phi as minus 0.6. Why? Because here phi we have to take as negative for leading power factor. Then just putting the values, we will get the load in kVA, then voltage per phase, then full load current, then open circuit voltage per phase. Now see here, we are putting the cos phi 0.8 as it is for leading power factor, but the sin phi must be with the negative sign because the reactive component will be below the reference. That's why we have to take the sin phi as minus 0.6, right? Then we will see that the regulation is with minus sign, right? That's why this synchronous impedance method is also known as what? Pessimistic method, because whatever the regulation we get here, that is always more than the expected values. Now the same for unity power factor. Now the condition is same, that's why the answer will remain same. So the percentage regulation with the same given data is 57.69% at unity power factor. Next question is question 2a, which is also for 6 marks. The question is an 11 kilovolt 3-phase star connected synchronous generator delivers 4000 kVA at unity power factor when running on constant voltage, constant frequency bus bars. If the excitation is raised by 20%, determine kVA and power factor at which machine now works. The steam supply is constant and the synchronous reactance is 30 ohm per phase. Neglect power losses and assume magnetic circuit to be unsaturated. So here, as per this question, we have to assume the excitation is raised by 20%, and according to that we have to determine the kVA rating and then power factor of the machine at new kVA, right? Okay. So first write down the given data. So as per the question, the applied voltage is that is line voltage is 11,000 volts. Then kVA rating is 4000 kVA when before the excitation is raised by 20%, and that is for unity power factor. Then synchronous reactance 30 ohm per phase. What we have to determine here? We have to determine the kVA when the excitation is raised by 20% and the power factor. Now continue to this. Equations to be used. So the voltage per phase, as we have already seen, it is equals to VL by √3. Then reactance drop, product of current and synchronous reactance, then generated EMF per phase is equals to square root of the phase voltage plus the drop, that is the product of IS and the square of that. Then the kVA rating is given by the product of RMS values of voltage and current. Therefore, phase voltage is calculated by putting the value of line voltage, that is 11,000 volt. So the answer is 6350 volt, the phase voltage. Then kVA rating is given of 4000 kVA. Then put the value of calculated phase voltage here. Then the as per the equation of kV is equals to VI, we can calculate the current, and that is the current due to the resistance, that is IR, is equals to 630 ampere. Then reactance drop, take the product of current and synchronous reactance per phase. So the current is 630, reactance is 30. Then the generated EMF per phase, put the value of phase voltage and the drop, that is IXS. So the answer is generated EMF per phase is 19938. First we will draw the phasor diagram with the values before the excitation, that is with V as a reference, and then with the values after the excitation, that is IXS drop. Also before the excitation, take V as a reference, so draw it parallel to the horizontal axis, then show the vector I lagging behind this V by an angle phi. Then show the in phase component IR in phase with the voltage V, right? Then show the vector for the drop IR axis at 90 degree to the applied voltage V. Then the induced EMF is equals to what? It is the vector sum of V and IR axis drop. So E is equals to the square root of V square plus IR axis whole square, that we already calculated. Then if the excitation is raised by 20%, then the active component of current, that is I cos phi, and that is indicated by IR here, it will remain same, but the reactive component of current, and due to that the drop IX excess drop will be different, and due to that the induced EMF will be different, right? So here the E dash, if the excitation is raised by 20%, is equals to the square root of V plus Ix excess whole square plus IR excess whole square. We'll see that on next slide. So here, if the excitation is raised by 20%, then the generated EMF per phase is equals to 1.2 multiplied by the induced EMF before the excitation, and that excitation is that induced EMF is 19938. So now the excitation is raised by 20%, so multiplied by 1.2. Right, so we will get the generated EMF per phase. Then as per the phasor diagram, E dash square is equals to V plus Ix excess whole square plus IR excess whole square. So using this equation we can determine the value of reactive component of the current, that is Ix, right? Then using this Ix we can find out the new value of armature current, and that is what? Square root of in phase component of the current, the square of that, plus the square of reactive component of the current. So I is equals to the square root of 630 square plus 7738.611 square, right? Now here 630 is the in phase or active component of the current, and 7738.611 is the reactive component of the current, and that is Ix. Right, so using the IR and Ix, here the new value of armature current is determined. Then using that we can find out the power factor, because we know that in phase component of current is equals to I cos phi. So IR is equals to I cos phi, we can take here. So IR is what? 630 ampere, that is calculated value, and that's why the power factor can be calculated as IR by I, right? So IR is what? 630 ampere, and I is 7764.212 ampere. So take the ratio of this, then we will get the power factor, and that is 0.08. And this is the inductive circuit, so we can say that the power factor is the lagging power factor. Now finally we can determine the new value of kVA. So take the product of voltage and new value of armature current, right? So finally we'll get the kVA, but that is in MVA. So that is the answer. Now the next question is question 3b, which is also for 6 marks. The question is, a 3-phase 10 kilowatt synchronous motor is connected to 1000 volt supply and has synchronous reactance of 10 ohm per phase. Find the value of minimum current and the corresponding induced EMF for full load condition. The efficiency of the motor is 80%. Neglect armature resistance. First, as usual, we'll see the given data. So here the motor output is given, that is 10 kilowatt. Then supply line voltage is 1000 volt. Then synchronous impedance as armature resistance is neglected, and that is equals to the synchronous reactance per phase, and that is 10 ohm. Then efficiency of the motor is given, that is 80%. Now what we have to find? We have to find out the minimum current, then TMF. Now you see the equations to be used. First, efficiency, we know that efficiency is motor output power divided by motor input power. Then motor input power is equals to, for three-phase system with the line values, is root 3 VLIL cos phi. Then impedance drop, we have already seen it right in the previous question, that is the product of I, Z. Here the armature resistance is negligible, that's why the impedance drop is equals to the product of current and synchronous reactance. Then phase voltage, that is voltage per phase, is equals to VL by root 3. Then induced EMF per phase, that we already seen, is equals to the vector sum of phase voltage and impedance drop. So EPH is equals to the square root of VPH square plus IZ square. Line induced EMF, as seen earlier for VPH, so it is equals to root 3 EPH, because we know that in three-phase AC circuits, line voltage is equals to root 3 times the phase voltage. We have the given data and we know the equations to be used, so by putting the values in the equation we can find out the answer, right? So first we will calculate the values and then we will see the phasor diagram. Motor input power is the ratio of motor output power to the efficiency. So put the value of output power and efficiency, then we will get the motor input power. Similarly, to find out the in-phase or active component of the current, take out the I cos phi from the equation root 3 VL IL cos phi and put the value of motor input power here, that is of 12,500 watts, right, and divided by root 3 VL. So we will get the I cos phi as 7.216 amperes, and this is the current, and this current is minimum when power factor is unity. So with this unity power factor, we can say that this I is equals to I cos phi. Then using this current, we can find out the impedance drop. So put the value of this minimum value of current and the synchronous reactance per phase. So that is the product of 7.216 and 10. So the impedance drop is 72.16 volts. Now this is the phasor diagram. The phase voltage is calculated by taking the ratio of VL to the root 3, right? So phase voltage is 577.35 volts. So that is taken as a reference. Then show the impedance drop, that is IZ is equal to 72.16 volts at 90 degree to this. Why? Because the armature resistance is neglected here, right? That's why the impedance drop can be shown at 90 degree to the voltage, and then the vector sum is what? EPH, right? Then we can show the current, that is minimum current I in phase with the voltage, that is VPH. Now you see the induced EMF per phase, which is the resultant of phase voltage and impedance drop. So first we will find out the phase voltage, then induced EMF by taking the vector sum of phase voltage and impedance drop, that is equal to square root of VPH square plus IZ square. Then using that we can find out the line induced EMF, that is root 3 times the phase voltage. So put the value of calculated EPH and get the line induced EMF, and that is the answer. Let's see the next question, question 3b, which is in all and which is also for 6 marks. The question is, a 3000 volt 3-phase synchronous motor running at 1500 rpm has its excitation kept constant corresponding to no load terminal voltage of 3000 volt. Determine the power input, power factor and torque developed for an armature current of 250 ampere if the synchronous reactance is 5 ohm per phase, right? Then we have to determine what power input, power factor and torque developed, and we have to neglect here armature resistance. Now we'll see the given data. So as per the question, the line voltage is 3000 volt, synchronous speed 1500 rpm, then synchronous impedance is equals to the synchronous reactance per phase, and that is 5 ohm, and it is why because armature resistance is negligible. What we have to find here, we have to determine the power input, power factor and torque developed for an armature current of 250 amperes. Now we'll see the equations to be used. Torque developed, that is equals to the ratio of motor input power minus armature copper loss divided by 2 pi ns divided by 60. So here we are taking the synchronous speed in rps, that's why divide the synchronous speed by 60. Then motor input power, that is equals to root 3 VL cos phi. Then impedance drop equal to IZ, and that is equals to IXS, because here armature resistance is neglected, that's why the impedance is equals to the synchronous reactance. Then phase voltage, that is equals to VL by root 3. Then power factor, that is cos phi, and then line induced EMF equal to root 3 times the phase EMF. So put the values and get the answer. So the phase voltage is 3000 divided by root 3, then we will get 1732.051 volts. Then get the induced EMF per phase equal to 3000 divided by root 3. Here the induced EMF per phase is calculated by taking the value of line voltage, that is equals to 3000 volt. Why? Because the excitation is kept constant and there is no load on the motor. That's why the induced EMF and the terminal voltage both are same. That's why here again we have taken 3000 volt as the line induced EMF, and that's why the induced EMF per phase is equals to 3000 by root 3, and that is same as the phase voltage. Input line current is equals to the input phase current is equals to 250 amperes, because we know that in star connection the line current and the phase current are same. Then impedance drop, put the value of 250 ampere current and synchronous reactance, that is 5 ohm. We will get the impedance drop, that is 1250 volts. Then internal angle, we can take it as 90 degree. Why? Because the armature resistance is negligible. So according to that we can draw the phasor diagram. Right, so assuming armature current lagging behind the supply voltage by an angle phi, so as shown in figure, that is phasor diagram. So take V as a reference, then show the current lagging behind V by an angle phi, right? Then show the vector, that is impedance drop ER at 90 degree to the current vector, and then the resultant is E, right? So according to the phasor diagram in triangle AOB, we can get the equation E square is equal to V square plus ER square minus 2 VER cos of 90 degree minus phi. So here put the values and we can get angle phi. Right, so first we'll get the sine phi and then take the sine inverse of that. So the angle phi is equals to 21.15 degree. Then using that we can determine the power factor, that is cos of phi, and that is 0.9326 lagging. So this is the answer. Next, motor input power is equals to root 3 VLIL cos phi. Just put the values. Then we will get the motor input power as 1212 kilowatt. Then torque developed. Now the motor input power is calculated. Armature copper loss is neglected here, right? So just put the input power and synchronous speed and get the torque developed in Newton meter. So that is the answer. The next question is question 3B for 5 marks. The question is a 400 volt 3-phase star connected synchronous motor has armature resistance of 0.2 ohm per phase, synchronous reactance 2 ohm per phase. It takes a current of 25 ampere from supply. Calculate the back EMF induced in the motor if it works at 0.8 power factor lagging. We have already seen this question in summer 2018, but still I have taken it here to observe the difference between the calculations when the conditions given are different. Okay, first we'll see the given data, that is supply line voltage is 400 volt, synchronous reactance per phase X is 2 ohm, R is 2.2 ohm, current is 25 ampere and power factor is zero point 0.8 lagging, and we have to determine the back EMF induced in the motor at 0 point 0.8 power factor lagging. Then equations that to be used here, impedance equal to square root of Ra square plus X square. Then impedance drop is the product of current and impedance. Then voltage per phase VL by root 3. Induced EMF per phase is equal to E square is equals to V square plus ER square minus 2VER cos of theta degree minus phi. And the line induced EMF can be calculated by taking the product of root 3 times the phase voltage that we already calculated in the above equation. Now we'll see the phasor diagram for lagging power factor. So here we are taking V as the reference, then show the vector for current lagging behind this V band angle phi. Then accordingly show the vector for ER, that is impedance drop IZ, and then the resultant will be the E. Right, so according to this phasor diagram, the E, resultant E is equals to the square root of V square, that is the reference, then plus ER square minus the product of VER, and it is multiplied by 2, and then cos of theta degree minus phi. Why theta degree minus phi? Because theta is the angle in between ER and I, and here theta is more as compared to the phi, so that's why we have to take the angle in between ER and V. That's why here we have to take theta degree minus phi. Then put the values and get the impedance, then impedance drop, then voltage per phase, then power factor is given as 0.8, so take the cos inverse of 0.8, then we get the phase angle, that is 36.86 degree. Then take the ratio of XS and RA, and then the tan inverse of that, we get the angle theta, that is 84.28 degree, and then the resultant angle theta minus phi will be 47.42 degree. Then put the values in. A square is equals to V square plus ER square minus 2 VER cos of theta degree minus phi. Then we get the resultant as 40,231, right? Then take the square root of that, and the induced EMF per phase is 201 volts. Then multiplied by root 3 to get the line induced EMF, and that is 348 volts is the answer. Now the same question, but the condition is given as zero point 0.9 power factor leading. The question is calculate the back EMF induced in the motor if it works at 0.9 power factor leading. In the previous question it was 0.8 power factor lagging. Right, so the same given data, but the cos phi is 0.9 leading. Then same equations, but the difference in induced EMF per phase calculation is that here we have to take the cos of 90 degree plus phi or cos of theta plus phi, that we'll see in phase diagram. So see here, we are assuming that armature current leads the supply voltage by an angle phi, so that's why I show the vector for current I leading the V by an angle phi. Then the angle in between current and ER is theta, which is less than 90 degree. Then the angle in between ER and V will be what? Theta plus phi. Right, that's why from phasor diagram the equation will be what? E square is equals to V square plus E R square minus 2 VER cos of theta plus phi. Theta plus phi is the angle in between ER and V, so that's why for the resultant E we have to take that angle. Put the values, get the impedance, then impedance drop, then voltage per phase, then phi by taking the cos inverse of 0.9, so phi is 25.84 degree. Then theta is equals to the tan inverse of ratio of XS by RA, that is 84.28 degree. Then the angle will be theta plus phi, that is 25.84 degree plus 84.28 degree, and that is 110.12 degree. So put that values, then we get the E square as 63,807. Then take the square root of that. So induced EMF per phase is 253 volts. Then to get the line induced EMF multiplied by root 3, and the answer is 438 volts, and that is at 0.9 leading power factor. Okay. Now the next question is question 4B for 7 marks of 25 HP 6 pole 50 Hz 3-phase induction motor has stator to rotor phase voltage ratio of 6/5. The stator and rotor impedances per phase are 0.25 plus J0.75 ohms and 0.173 plus J0.52 ohms respectively. So what these are? These are the stator and rotor impedances. Find the starting torque exerted by the motor when an external resistance of 1 ohm is inserted in each phase of rotor winding. The motor being started directly on the 400 volt supply system. Assume star-star connection. So here we have to find out the starting torque. So to determine the starting torque, first we have to find out the output power, synchronous speed. Right? So we'll see that. So voltage per phase is calculated by taking the ratio of VL by root 3. So it is 400 by root 3 is 231 volts. Then rotor to stator phase voltage ratio is given, that is 5/6. Then according to that we can calculate the equivalent resistance of the motor as referred to the rotor. and that is RO2 is equals to R2 plus K square R1. R2 is what? Rotor resistance. R1 is the stator resistance. So as per the given data, rotor resistance is 0.173 and the stator resistance is 0.25 and K is 5 by 6. So the RO2, that is resistance of the motor referred to the rotor, is 0.3466 ohm. Similarly, the equivalent reactance of the motor as referred to the rotor is XO2 and is equal to x2 plus k square x1. So put the values, then we will get XO2 is equals to 1.0408 ohm. Then by putting that RO2 and XO2, we can get the equivalent motor impedance referred to the rotor circuit, and with external resistance of 1 ohm per phase inserted in the rotor circuit. That's why ZO2 is equals to square root of RO2 plus 1 whole square. So here plus 1 indicates that 1 ohm of external resistance is inserted in the rotor circuit, and then XO2 is 1.041. So the resultant equivalent impedance referred to the rotor circuit is 1.7 ohm. Then using that we can find out the induced EMF in rotor at standstill, and that is E2 is equals to V1 multiplied by K. V1 is, that is phase voltage, that is 231 multiplied by 5 by 6 is the stator to rotor ratio. So it is 192.5 volts. Then rotor current is equal to E2 by ZO2. So the rotor voltage divided by rotor impedance. So it is 192.5 divided by 1.7 is equals to 113.23 amperes. Now the rotor copper loss is equals to 3 times I2 square R2. Here we have to find out the total copper loss. That's why multiplied by 3 as it is for 3-phase circuit. So it is 45093 watts. Then rotor power input at standstill, P2 is equals to total rotor copper losses is equals to 45093, and synchronous, it is unit is what? Synchronous watts, since sleep is equals to 1. Then we can find out the synchronous speed ns is equals to 120 f by p, so it is 1000 rpm. And then putting that all the values, we can find out the starting torque TST is equals to 9.55 multiplied by P2 by NS, and it is 430.6 Newton meter, and it is the answer. The next question is question 4a for 6 marks. The power input to the rotor of 440 volts 50 Hz 6 pole 3 phase induction motor is 80 kilowatt. The rotor EMF is observed to make 100 complete alterations per minute. Calculate the sleeve, the rotor speed, the mechanical power developed, the rotor copper loss per phase, and the rotor resistance per phase if the rotor current is 65 ampere. So as per the question, the given data is line voltage is 440 volt, number of poles 6, input power 80 kilowatt, and rotor completes 100 completes alterations per minute. And we have to find out the sleeve, the rotor speed, the mechanical power developed, the rotor copper loss per phase, and rotor resistance per phase if the rotor current is 65 ampere. So as per the question, the supply frequency is 50 Hz and 100 alterations per minute are given. So using that we can find out the rotor EMF frequency, that is F dash is equals to 100 by 60. So it is 1.667 cycles per second, that is Hertz. And the sleep is the ratio of F dash and F, so it is 0.03. Then synchronous speed is 120 F by P, P is 6, so it is 1000 rpm. Then put that in equation of rotor speed is equal to 1 minus S multiplied by NS, and that is 970 rpm. Then power input to rotor P2 is equals to 80 kilowatt is given. So using that we can find out the rotor copper loss per phase, as it is asked to find out per phase, that's why divided by 3 and multiplied by sleep S, then we get the rotor copper loss per phase as 0.8 kilowatt. Then mechanical power developed is equals to P2 multiplied by 1 minus S. P2 is the rotor power input and it is 80 kilowatts. So multiplied by 1 minus 0.03. So it is mechanical power developed 77.6 kilowatt. Then using the rotor copper loss per phase in watts, we can find out the rotor resistance per phase R2. So R2 is equals to 0.8 multiplied by 1000 divided by 65 square. So it is 0.189 ohms. Now let us see the next question. Question 4a, which is for 5 marks. The question is, determine the slip at maximum torque and ratio of maximum to full load torque for a 3-phase star connected 6.6 kilovolt 20 pole 50 Hz induction motor. Its rotor resistance is 0.12 ohm and standstill reactance is 1.12 ohm per phase. The motor runs at 292.5 rpm at full load. So what we have to determine here, slip at maximum torque and ratio of maximum to full load torque. First we'll see the given data. So as per the question, the line voltage is 6.6 kilovolt, number of poles 20, then rotor resistance, that's why R2, it is what? Rotor resistance, okay, that's why it is indicated as R2 and it is 0.12 ohm per phase. Then standstill reactance, that is X2 is equal to 1.12 ohm per phase. Then full load speed is 292.5 rpm and we have to determine here slip at maximum torque and ratio of maximum to full load torque. So the synchronous speed, we know that what is the equation, ns is equals to 120 f by p. So put the value of f and p and synchronous speed is what, then 300 rpm. Then full load slip is calculated by the ratio of ns minus nf to ns. What is ns? Ns is the synchronous speed, so put it as 300 rpm. Then full load speed is given as 292.5, so take the ratio of that. Then the full load slip is 0.025. Then with this we can find out the slip corresponding to maximum torque. So S max is equals to the ratio of R2 by X2 and that is 0.101107 and that is the answer for slip corresponding to maximum torque. Then we have to find out the ratio of maximum to full load torque. So put the maximum slip and full load slip. Then we can have a ratio of maximum to full load torque, that is 2.256. This is the answer. The next question is question 4a, which is in OR and it is also for 6 marks. The question is, the rotor resistance and reactance per phase of a 415 volt 4 pole 50 Hz 3-phase induction motor is 0.03, 0.024 ohm and 0.12 ohm respectively. Find the speed at maximum torque. Also find maximum torque in Newton meter. Consider ratio of stator turns to rotor turns as 1. So first see the given data. Voltage is 415 volts, number of poles 4, rotor resistance 0.024 ohm per phase, as it is a 3-phase induction motor and we know that in 3-phase induction motor there are two constructional parts, rotor and stator. So the rotor parameters are indicated by the suffix 2 That's why R2 here indicates rotor resistance and X2 indicates rotor reactance, and both are per phase value because this is a three-phase induction motor. Then what we have to determine here, speed at maximum torque and maximum torque. First find out the synchronous speed by using the equation 120 F by P. So put the value of frequency and number of poles. So we'll get the synchronous speed as 1500 rpm. Then sleep corresponding to maximum torque by taking the ratio of R2 and X2, and it is 0.2. Then speed at maximum torque, so put the value of sleep corresponding to maximum torque in the equation, ns in bracket 1 minus s. So instead of, in place of s, put here s max. So we'll get the speed at maximum torque, and that is 1200 rpm. As in question it is given that the ratio of rotor turns to the stator turns is 1. So using that we can calculate the rotor induced EMF equal to KE1. So that's why it is equals to 1 multiplied by 415 by root 3. Stator EMF is given, that is 415, and it is the line voltage. So get converted into phase voltage, and that is 415 by root 3. Turns ratio is 1. That's why the rotor induced EMF per phase is 240 volts. Then by using the equation K dash E2 square divided by twice X2, we can find out the maximum torque. So put the value of K dash as 3 by 2 pi ns divided by 60, and then E2 and X2, we will get the maximum torque, and that is 4560 Newton meter, and this is the answer. Now the next question is question 5, which is for 10 marks, and that is of circle diagram. So the question is a 5 kilowatt 400 volts 4 pole 50 hertz delta connected motor gave the following results, and it is assumed that the stator resistance is 1.6 ohm per phase. Now the data by no load test is voltage 400 volts, current 3.1, and power is 350 watts. The data by block rotor test, it is voltage is 52 volts, current 7.6 ampere, and power is 440 watts. What we have to do here, we have to draw a circle diagram to the scale, and we have to determine the full load efficiency. So let us see the given data first. So as per the no load test, no load voltage is 400 volts, no load current is 3.1 ampere, and no load power is 350 watts. So using that we can find out the no load power factor, and that is equals to P0 by root 3 V0 I0. So no load power is given, that is 350, then no load voltage is 400, and no load current is 3.1. So put that values, so we'll get the power factor, that is no load power factor as 0.163. Then using that find out the no load phase angle. So take the cos inverse of 0.163. So the no load phase angle is 80.62 degree. Now short circuit current with normal voltage applied across the stator can be calculated as ISC is equals to the short circuit current 7.6 multiplied by no load voltage to the short circuit voltage, that is 400 by 52, and that is the current, that is short circuit current with normal voltage, and it is 58.46 amperes. right? So using that we can find out the short circuit input with normal voltage, that is PSC, and that is equals to 58.46 divided by 7.6 whole square multiplied by 440. Right, what is here 58.46? It is the short circuit current with normal voltage, and what is 7.6? It is the current that we take it from the short circuit test readings, right? Then short circuit power factor cos phi SC is equals to PSC by root 3 V naught ISC. So just put the values and give the short circuit power factor as 0.64. Then short circuit phase angle, take the cos inverse of 0.64. Then we get the short circuit phase angle as 50.20 degree. Here the values are not as per the given data, so that may be due to some inaccurate values in questions. Now short circuit current with normal voltage applied across the stator. Okay, that we have seen. So now we have to decide the current scale, and that is 1 centimeter is equals to 5 ampere. So here we are taking 1 centimeter is equals to 5 ampere. By using the results obtained from no load and block rotor test on 3-phase induction motor, we have calculated the no load phase angle phi naught and short circuit phase angle phi SC, which are used here to draw the circle diagram. So with O as origin, take OV along the y-axis, then with O as origin, draw OO dash, that is equal to no load current at an angle phi naught to V, that is it is lagging behind V by an angle phi naught. Then with O as origin, draw OA, that is equals to the short circuit current with normal voltage, and that is to be drawn at an angle phi SC to V. Then draw OF perpendicular to OD. Then from O dash, draw a line O dash G parallel to OF. Then to get the center of the required circle, draw a perpendicular to the line O dash G, O dash A. First join the line O dash A, and then take a perpendicular to line O dash A that will bisect the line at point B, and then it will intersect the line O dash G at C. So with C as the center and O dash C as the radius, we can draw the semicircle, and that is shown on the next slide. So here with C as the center and O dash C as the radius, we have drawn a semicircle. Then at an angle phi 1, draw or join OH. So to get the point H, draw a line parallel to O dash A, that is output line, that also represents the rotor current referred to the primary side, that is I1 dash, right? So OH will indicate the current I1, and that is at an angle phi 1 to V. Then to estimate the maximum output power, maximum torque and maximum input power, draw the intercepts to the circle diagram. So here first draw the points O dash D. So O dash D line indicates the torque line. Then the O dash A is already joined, and the O dash A indicates the output line, right? So to get the maximum output power, drop perpendicular from point H, and then that will cut the lines O dash A, O dash D and O dash C at the points K, L, M, right? So the HK, it is the vertical intercept HK indicates the maximum output power. Now to estimate the maximum torque, draw a line parallel to the torque line, then that will in, intersect the semicircle at O dash, that is it will be tangent to the semicircle, and then O dash O will indicate the maximum torque, right? Then to get the maximum input power, drop a perpendicular from point A, and means what, how to get the point A, draw a line parallel to the O dash Z or OF, then that will be tangent to the semicircle, right? That will cut the semicircle at point A. Then the vertical intercept AF will indicate the maximum input power, right? Also it will indicate the total losses. EF indicates the no load losses, that is fixed losses. Then AD rotor copper loss, and DE stator copper loss, right? So the points HK, then HL, HM and HN. So these are the energy components of the line current I1, and that will see how these are used to calculate the sleep, power factor and efficiency at full load. So to determine power scale, a perpendicular AF through A is drawn, that we have already seen. So AF represents the total input on short circuit with normal voltage, which is 26034.132 watts. Since AF is equals to 7.15 centimeter, we can measure it by scale, and it is 7.15 centimeter. So the power scale is what then? 26034.132 divided by 7.15, and that is 3641.137 watts per centimeter. So at full load we can calculate the power factor by taking the ratio of NH, that is the energy component of the current I1, divided by OH. OH is what? That is the line current I1 at an angle phi 1, right? So by taking the ratio of that, we get the power factor as 0.9. Then output can be calculated by KH and multiplied by power scale. So KH, measure it in centimeter by scale, so it is 2.15 centimeter, and multiplied by power scale, then we will get the output in watts. Then find out the efficiency by taking the ratio of KH to NH and multiplied by 100. So we'll get the efficiency, and the ratio of that KH by NH is 2.15 divided by 4.61 is 0.466, multiplied by 100, then we'll get the efficiency, that is 46.6%, and that is the answer. So I think all the questions are clear to you, and if you are having any doubts, any confusion, then you can contact me, you can call me, right? Thank you.